Okay, then hello everyone. It's my very great pleasure to welcome all of you to today's online seminar on interval methods in control engineering. And today we'll have Amre Alanwar with us, who is a professor with the chair of cyber physical systems at the School of Computation, Information and Technology at the Technische Universität Munich. And he has been there since September 2023. That means quite recently he joined the team. And before that, he was a professor at Constructor University at Bremen. That means quite close also to my place of Oldenburg. And yeah, before that, he received his PhD degree at the Technische Universität München in Munich in 2020. And before that, he was a research assistant at the University of California in Los Angeles. And he has received numerous prizes, best paper awards for his research activities. And one of his current research activities concerns the reachability analysis for logical systems using logical zonotopes and their polynomial extension. And we're now looking forward to your presentation.
Yeah, thank you so much for the invitation and for the introduction. It's my pleasure to be here today and present to you my work. I hope you enjoy the talk. So today I will talk about reachability analysis for logical systems using logical zonotope and their polynomial extensions. As a motivation, consider that we have a Boolean function or digital circuit and we have uncertainty on the input, which means this line can be 0 or 1. And given that we have uncertainty on the input, the output will be uncertain and will consist of set of points. We would like, as usual, to propagate the set of points and check the intersection with the unsafe set. We call this, as you know, of course, reachability analysis. But how to represent sets of points in discrete manner and how to propagate them forward, this is the question of the talk. Also consider that we have a logic that governs the intersection between four cars. And we have uncertainty in this logic, which means the car might arrive or might not arrive. So B2 might be 0 or 1. Can we handle such uncertainty on a large scale? This is another question for the talk. Further motivation in cryptography, consider that we have plain text ciphertext attack, which means we have message and we have its encrypted value, or we call it ciphertext, and we aim to find the key that does the matching between the message and the ciphertext. The traditional exhaustive search is to try key by key until you find the value that encrypts the message to the encrypted message or the ciphertext. We advocate for another direction using sets, which consist of the following. Consider that we put sets of keys, like multiple keys, multiple possible keys in a set, and then do set operation between the message and the key. Given that we have started by multiple keys, we will get set of encrypted messages or set of ciphers, as shown here. And then the message and the cipher are given. We check the containment of the given cipher inside the ciphertext. If it's not inside the cipher set, we can neglect the whole key set. So we are trying multiple keys at once, and instead of trying one key and then the other. For example, if you have 2 to the power 16 key, we can possible keys, we can divide them into 2 to the power 15 and 2 to the power 15, and then put this 2 to the power 15 on the left on the key set, and then check the containment of the cipher inside the cipher set. If it doesn't contain the cipher, the given cipher, we can neglect the whole branch, and we can keep dividing the sets or the possible keys into smaller keys until we reach the key. But how to represent set of keys, how to do the set operation, for all of this, we introduced logical zonotope, which consists of the following, inspired by the traditional zonotope in the continuous domain. So it consists of a point, C. This is the XOR symbol in the talk. So it's a multiple XOR or summation of XORs between generators ended with beta, where beta takes all the values of zeros and ones. For example, if we have two generators, we will have beta 0, 0, 0, 1, 1, 0, and 1, 1. So if you have two generators, as I have said, you will start by beta 0, 0, and we will have single point. And then we turn on the first generator by having the beta as 0, 1, as the 1 is ended by the first generator and the 0 is ended with the second generator. So we are turning on the first generator. And then we turn on the second generator by having the beta 1, 0. And then we turn on both generators by having the beta 1, 1. So as shown here, we have represented 4 points using 2 generators only. And this is the beauty of logical zonotope, that you can represent up to 2 to the power gamma binary vectors using gamma generators only. So you can think of the generator as the reduced space, and we are doing reduced representation. Let's take an example. If you have a C here, and this is the generator, which consists of one generator only, and this is the symbol for logical zonotope. So to convert it in 2 points, we will have the beta as 0, and we will XOR the C with the generator. We will get 0, 1, and then we will XOR the C with the second generator to get 1, 1. So we have represented 2 binary vectors using only one generator. If we have 2 generators here, G1 and G2 here, and this is the C, the beta will be 0, 0, 0, 1, 1, 0, and 1, 1. So we have represented 4 binary vectors using 2 generator vectors only. And it's not only about representation, but also you can do computation on the reduced space or the generator space. We define, inspired by the Minkowski sum in the continuous domain, the Minkowski XOR, and this is useful when you would like to try all the possible combination of keys. Minkowski XOR, we define it as all the possible XORs between all the points from the first set to all the points in the second set. So XOR between every point in L1 with every point in L2. To do this in normal points, you need 2 for loops. And if we consider one logical zonotope, in the worst case consists of 2 to the power gamma 1 points, and then the second one 2 to the power gamma 2, where gamma is the number of generators, and then n, which is dimension of the vector. We need a complexity of n 2 to the power gamma multiplied by 2 to the power gamma. Instead, in logical zonotope, it's enough to just XOR the C's and concatenate the generators, and it's equivalent to for loop over all the points. So we are reducing and simplifying the computation in the reduced space or the generator space. Let's take an example. If we have here L1 and L2, and this is the first generator, and this is the first generator in the second zonotope, and the second generator in the second zonotope. If you would like to do Minkowski XOR, we just XOR the C's, where this is C1 and this is C2. So we will XOR the 2 C's and concatenate the generators. If you would like to convert it in 2 points, you will get 4 binary vectors, 0, 0, 0, 1, 1, 0, and 1, 1. And if you do it in point domain by converting each logical zonotope from the beginning in 2 points, and then do the Minkowski XOR by 4 loops over all the points, you will get the same 4 binary vectors. We can also do NOT, which means inverting all the points inside a set, which usually takes for loop over the number of the sets, over the number of the points inside the set. And in logical zonotope, it's enough to just XOR the C with a vector 1 and keep the generator untouched. For example, we have here one C and one generator, and we XOR the C with 1, we will get 1, 0, 0, 0 as 2 binary vectors. In the point domain, if you convert L1, we will get 0, 1, 1, 1, and you for loop over all the binary vectors, you will get 1, 0, 0, 0, equivalent to the logical zonotope operations. Until now, we have done XOR and NOT, but can we do more than Minkowski XOR and NOT? The answer is yes, with a computation complexity. So we can do also Minkowski AND. However, the AND is over-approximated, which means if I have the exact value 0, 1, 1, 1, we might add a value 1, 0 as well. So this is the added binary vector due to the over-approximation in the binary domain. And the operation is done by ANDing the centers, and then ANDing the center with each generator, and then AND each generator with each other, which quite complex and leads to over-approximation as well. Given that we are able to do the AND and the NOT, we are able to do the NAND, which is not AND, as you of course know. And the NAND is a universal gate, which means you can build any logical circuit or Boolean function using the NAND gate. So we will be able to do the OR and the NOR using the NAND gate. And given that we have done all the logical operation using the NAND gate, we can go through the main theorem in the first paper, which says the following. If you have a function, logical function f, the reachable region computed in the generator domain using logical zonotope over-approximates the exact reachable region due to the over-approximation in the NAND and the AND. We can also do semi-tensor product in the generator domain, but let me first define what semi-tensor product. This is a symbol for semi-tensor product, and it's mainly the matrix Kronecker product with identity matrix multiplied by another matrix Kronecker product by the another identity matrix, and the size of the identity matrix is shown here. So we can do semi-tensor product between logical zonotopes similar to the ANDing. Instead of performing ANDing, we will do semi-tensor product between the generators. But can we have exact ANDing instead of the over-approximation? And the answer to this takes us to looking into the ANDing proof, which is quite simple. If you have a point Z1 inside the first logical zonotope L1, and you have Z2 inside the second logical zonotope L2, so we will AND the both points, which mean ANDing, it's like multiplication. You AND each term with each term. As you can see here, there is beta ANDed with another beta. In the logical zonotope, we are over approximating this term by 1 beta, as if you multiply zeros and ones and zeros and ones, you can represent them by 1, 0, and 1. However, it's an over approximation. To do it exactly, you must allow for ANDing between the factors, betas. For example, you must allow for a set that allow, we call it alpha instead of beta, and it allows the ANDing between the factors. So you can have alpha 1 ANDed with alpha 2, which is similar to beta 1 ANDed with beta 2. And this must be allowed inside the set representation. So this leads us to the polynomial version inspired by the polynomial zonotopes in the continuous domain, which consist again by a C and then some dependent generator matrix multiplied by or ANDed by the generators, power to the exponent matrix, and the power here is basically turning on and off the generator. It's either 0 or 1. For example, if we have, this is the C, and this is the G, and this is the exponent matrix, to write this set out, we take the C as it is, and then we have each line in this exponent matrix represent the alpha. So the first line represent alpha 1, and the second line represent the second factor, which is alpha 2. So the first generator takes the first vector inside the exponent matrix, which means there is alpha 1 and there is no alpha 2. So this result in 0, 1, 1 ANDed with alpha 1 only. And then 1, 1, 1 ANDed with 1, 1, which is alpha 1, alpha 2. So this is the polynomial representation of the polynomial logical zonotope. And as you can see, we allow for ANDing between the factors. And to do the Minkowski XOR, which as I defined before, all the possible XORs between the two sets, it's enough to concatenate the generators and have the exponent matrices on the diagonal as shown here. However, there is still a problem. In the binary domain, if you have a set B1, which consists of 1 bit, C and G, and the exponent matrix here. So, and you would like to do B1 XOR with B1. If you look into the XOR table, anything XORed with itself should lead to 0. However, if we apply the Minkowski XOR, B1 XORed with B2, we will have G1 concatenated with itself and the exponent matrix 1, 1, which will lead to 0, 1 points. However, B1 XORed with B1 should lead to 0 only. This is known in the literature by the dependent or the dependency problem. To solve this, let's take a look and get an idea from the sparse polynomial zonotope in the continuous domain. If you have alpha 1 and alpha 1, the same alpha, and ANDed by two generators, you can take the alpha as common and XOR the generators. However, if you have alpha 1 and alpha 2 different, you can just concatenate the generators and concatenate the alphas. So this is the dependent factors and this is the independent factor. So by factor, I mean the alpha. So the alpha 1 is dependent on this alpha 1, and this will show up if you XOR the set with itself. So inspired by the traditional polynomial zonotope, we need again to identify the factors by having IDs for the factors and perform the operations based on the ID. If the ID are similar, we deal them in a specific manner. If the IDs are different, we deal them in a different manner, like the Minkowski XOR. For this, we extend the polynomial logical zonotope definition with ID, which basically identifying the dependent factors. And for this, before the operation, we need to do some operation called merge IDs. So if you have polynomial logical zonotope where this is the C, this is the G, and this is the exponent, and this is the ID, and the ID here is 1 and 2 for alpha 1 and alpha 2, and here 1 and 3 for alpha 1 and alpha 2. We need to do merge ID, which means adding the missing ID from each logical zonotope, polynomial logical zonotope to the other. So the 3 is missed here. So we add the 3 and add a 0 row in the exponent matrix, which correspond to the third ID. And here we add 2 and add a 0 in the exponent matrix, which correspond to the added ID. And by doing this, we are able to, we call it exact XOR instead of Minkowski XOR, again, inspired by the name exact sum in the continuous domain. And the formula is concatenating the generators and concatenating the exponent matrix instead of putting them on the diagonal. And we have also exact ANDing. It is still complex, but it is exact in this case. We AND each generator with each generator and have the exponent matrix in a specific manner as shown here. And as I mentioned, the polynomial logical zonotope is able to do the exact ANDing and the Minkowski ANDing, depending on your needs. Now the weak points in the work that need still enhancement, and there are a lot of open doors to enhance. So if you would like to convert points into logical zonotope, we take the first point as the C and then XOR every point with each C to get a new generator. This is inspired by the truth table. If you have 3 generators with 3 betas, you will notice that the first line consists of only the C, which is the first point already. And then each line has the beta alone, has 1 beta alone. So for example, line 2 has beta 1 alone. So we can assign another point here by having generator XORed with C, and the generator is already S XORed with C, so the C will be XORed with C, which means 0, and you will end up with the second point. Similarly, you can have the third point and the fourth point. However, the drawback of this operation that it results in a huge number of generators, which is not the idea of logical zonotopes. So we need the best representation for sets of points. For this, you might do reduce or simplify, which is basically converting the zonotope into points and removing each generator and check the effect of removing the generator. This is still a complex operation, but you can do this offline to build the representation, the most efficient representation before starting your operation. So remove each generator and check the effect of removing the generators. If the points are the same, you can safely remove the generator. I need also to briefly mention the binary decision diagram, which we compared against. So it's introduced in mid-80s, and it's a data structure for representing Boolean function. And given a proper variable ordering, BDD can evaluate Boolean functions with linear complexity in the number of variables. However, finding the proper ordering is a very difficult problem. And you can perform decision diagrams as shown here. You start by a specific variable and then check the path. If this C is false, then the whole formula is false. If it's true, you need to check the second variable. If it's true, you need to check the third variable until you reach the conclusion that the whole formula is true. And you can reduce this decision diagram to have a reduced logic. However, as I mentioned, finding the best order for these variables is a very difficult problem. There is also Boolean control network, which consists of some which can represent the following dynamics. We have logical function for state and the input, and the main theorem in the Boolean control network that any dynamics can be represented by something called structure matrix. And this structure matrix is semi-tensored with the input and semi-tensored with the state, where the X is semi-tensored, is the semi-tensor of all the X's, and the U is the semi-tensor of all the U's. So if you would like to do reachability analysis, you can take all the possible U's and all the possible X's with the structure matrix. However, building the structure matrix for high-dimensional Boolean function is not an easy task, and it needs a lot of computation and techniques. Now to the evaluation. We have evaluated the logical zonotope and polynomial logical zonotope in multiple problems. The first one is the intersection crossing protocol that governs the intersection between four cars. Consider that we have a logic as shown here, and we have uncertainty on the input, which means the input can be 0 or 1. How to predict and compute the P and the C? This is the computation time for zonotope, polynomial zonotope, BDD, and binary decision diagram and Boolean control network. The zonotope is the best execution time as shown here. However, it's not exact. It adds 3 points in the beginning, 2 points in the following steps. The polynomial zonotope is slightly worse. However, it's exact. The BDD goes to very high execution time when we increase the number of steps. And I would like to comment on this 13 and 14 here. This because the BDD, I couldn't find a way to solve the dependency problem, which is shown here. We have the BI and the BI here. They are dependent on each other. I couldn't solve it from one iteration to another iteration using the BDD and BCN. This is my explanation for why the BDD is not exact in the first line. And then we have also tried it with high-dimensional Boolean function, in which we have 10 possible vectors with B1, B2, B3. And this is, I think, it was 10-dimension vector. The BCN is very difficult to build the structure matrix, so I couldn't build it. So I compared only with BDD. The star means the execution time is very huge. It takes forever, so I just multiply the number of iterations by the execution time of one iteration. The zonotope almost failed because it adds 300 points, as you can see. However, the polynomial logical zonotope is exact with good execution time. So the lesson that zonotope might not be the best option if you have a lot of ANDing with high dimensional Boolean functions. We also start simple in the key search and cryptography by having a linear feedback shift register, which is a basic building block for many stream ciphers like A5 and so on. And the idea that at each clock there is XOR that takes the value from the end to the beginning and then end up with one bit outside, which is a stream key, which will be XORed with the message to get the cipher. And the idea to use the logical zonotope here by having one bit for each logical zonotope and have the representation of the uncertain bit. If you know, in quantum we have the Q bit, which represents the 0 and 1. Inspired by the same idea, we can here have the uncertain bit, which consists of 0 and 1 in the same time, which is a set of points. And we explore both directions with the same operation and check. As I mentioned, we try multiple keys at once by setting some bits to certain and some bits to uncertain. Uncertain means some bits are assigned to logical zonotope with zeros and ones, and the other bits are certain, which means 0 or 1. By having this, we will have set of keys, because sorry, I forgot to mention that the key is the initial value of the register. This is usually in cryptography that they use the initial value as a key. And then we will do the set operation, which is set of XORs. We start here very simple in cryptography. I didn't try a lot of cryptographic techniques and so on. I was just exploring the direction of exhaustive search using logical zonotope by trying multiple keys and one message or set of messages, and you do set operation and check if the given cipher here is inside the cipher set. And if it's not, we neglect the whole key set and never try this direction again. So the exhaustive search here takes forever, as expected, especially with key size 120 bits. And the logical zonotope was able to get it in 7 seconds on MATLAB, which is not the best environment for trying cryptography, of course. So I would like to acknowledge my collaborators and co-authors on these 2 papers. And today I have represented logical zonotope as a set representation, polynomial logical zonotope. I have done operations on the generator space, and I have shown some application for logical zonotope. This is the repository for the logical zonotope and polynomial logical zonotope. You can play with it on MATLAB, and there is one student who was interested in implementing it in Python. So you can find also the Python representation of logical zonotope, and this is my website for more information. Thank you so much.
Okay, and many thanks to you for a very interesting presentation. And yes, we already have the first round of applause here in the audience virtually. And definitely there will be some questions. Who wants to start? Luc?
Yes, if possible. So thank you for the talk. Just a small question, because I'm not sure I've understood about the logical zonotope. So it is a subset. So the component of zonotope are only Boolean numbers, yes?
Yeah, it's binary vector, 0 and 1 only.
with 0 and 1, because I was not sure, because I have the feeling that at the beginning of the talk, when you have shown a zonotope, a logical zonotope, I had the feeling that you have more than 2 components. So maybe you can show again one of the zonotope, because you have shown just at the beginning, and that
Yeah,
was
sure.
confusing for me.
Yeah, sorry for that.
Yes, because sometimes you show zonotopes like here, or just at the beginning, maybe.
This is the example of logical zonotope, for example.
Yes, so yes, so it's always when you show a graphic of a zonotope, you have some picture with zonotopes sometimes. Yes, like this one, for instance, like this one. So I would like to know here, the components are.
Yeah, the component are the C and the generator. The C
Okay.
here is not the center, it's just a point inside the logical zonotope. And
Okay. Yeah.
yeah, sure.
Yes. So n equal to what here?
N
N
is the dimension of the C and the generators, and the X. So
in your
it's
picture it is 2.
in my picture it can be anything.
Okay. It's okay. It's
Because
conceptual. Yes.
this generator is another dimension. It can be any dimension.
Okay. So So that's clear. Thank you. That's
Yeah, thank you so
I've
much.
understood. Okay.
Thank you.
Okay, do we have any further question? Okay, maybe let me continue. What you have shown during your talk is a very interesting approach for reachability analysis. Did you also handle approaches, or do you plan to handle approaches that allow for optimization? I'm just thinking into the direction of finding, for example, the most simple representation of a Boolean function that is trying even to minimize pessimism in the evaluation, to get rid of, for example, the cause of dependency effects, or also to reduce the complexity of Boolean representations that could be implemented in a classical way. Are there any ideas in order to use your logical sonotope approach into that way?
Yeah, we didn't until now investigate the optimization or the control of Boolean function using logical zonotope, but it's of course on the table, but we didn't have time until now to investigate it. And of course, it's a very nice idea because you can perform the control on the generator space, which is the reduced space. So it should theoretically end up in a good execution time, as you are controlling in the generator space instead of the normal points. Also, if you have sets of points, how to propagate and control them, it's not an easy task.
Yeah, yes, definitely, but is hopefully, like it's just recommended at the end or suggested at the end, also hope that your approach will then help you to speed up the execution time as hopefully some orders of magnitude in comparison as to classical optimization techniques.
Yeah, I hope so, yeah.
Yes, the other question that I have is what you mentioned at the beginning and also at the end in the application scenario with this crossing, the crossing example that you had shown for the vehicles. There you at the moment just investigated the Boolean part. But a classical cyber-physical system would also have to take into account some of the variables that are continuous. For example, let's think about position inaccuracy, position uncertainty, which will then be taken into account at the end, for example, in a control strategy. Are there any ideas or recommendation how to interface the Boolean part on which you have focused today with classical sonotopic procedures where you have real valued quantities?
It might be, the answer might be the hybrid zonotopes, but I'm not sure. I'm not 100% sure for the answer. We didn't investigate this direction also, sorry. But the answer might be hybrid zonotopes because it allows this hybrid, the hybrid component between I'm not sure if you are aware of hybrid zonotopes, but it consists of, it represents the values in the continuous domain, but it allows the beta to be separate zonotopes. Instead of one zonotope, you can have separate zonotopes, and you can jump between the transitions, which is the typical behavior in hybrid systems, that you can jump from one behavior to another behavior. And the answer might be hybrid zonotopes. I'm not sure if logical zonotope would help here. I don't know yet.
Yeah.
But
okay, but yes, maybe I'll have a look at this because it could be very interesting to have this combination between logical operators on the one hand and classical continuous valued other quantities that appear simultaneously in a closed loop control system.
yeah, exactly. It will be a very nice paper, yeah.
Okay, let's have a look at the list of participants. Do we have any further question? If so, please unmute yourself and go ahead. This doesn't seem to be the case. Then again, many thanks for your talk. Many thanks also for answering the question that you have received. And yes, to all of you, have a nice weekend and see you soon at the end of February for the next seminar.
Thank you so much for the invitation and for attending the talk. I really appreciate your time, and it was my pleasure to present my work. Thank you so much.
Thank you. Bye.
Bye.
Bye-bye.